Hello everybody to clip 2 of part 2 in modern wireless communication and applications. This part 2 is related to digital communication, and now we are in clip 2. So we have arrived to this slide about analog and to digital converter, and we mentioned that in order to convert our analog signal to digital format, we need two steps. The first step is the sampling, so we take samples in time. And the second step is quantization, where we quantify the number of levels per sample. Now in the sampling, so usually we take the samples every ts second. It is called sampling time, and the sampling rate is the inverse of the sampling time, so it is 1 over ts. And about the quantization is the number of levels that we agree about each sample. And of course, as we increase the number of quantization levels, as more accurate or less quantization noise is added to the original signal or to the quantized signal. So you can see here that we have analog signal, and we take samples. For example, we assume it here. We take the sampling time is 0.1 second. So you can see the stars here. So we see the sampling time that we take, and this is the sampled signal. This is the sampled signal. Of course, it is sampled and like a sample and hold. So it becomes that it is fixed for the whole sample period. So when we take this sample, so it becomes like this one, sorry, this one, and this also will be like hold in this level, and now this will be in this level, and so on. So after the sampling of the signal in time, then we need to quantize this signal, because this signal can be any level, as we mentioned in the previous clip, that for example from 0 to zero point 0.7 here, so we have infinity number of levels if it is in analog format. So for example, if we divide it into like 8 level, from level 0 until level 7, then we need to round each sample to its closest level or allowed level. Of course, we can divide it into like if it is divided to be represented by 4 bits, it means that it will be divided into 16 level. If it is, for example, 8 bits, it means that it is 256 levels, and so on. After this quantization, we can convert now each sample, each quantized sample, to its digital format. So for example, this sample was like rounded to level 4, as you can see here. So it is at level 4, and 4 in digital format is 100. So you can see that we can convert them according to this requirement. So if we are going from this direction to, so it is 1 1 like 0 1 1, so it is or 0 0 1, and so on. So we can convert the signal, each sample, to its digital format. It is called pulse code modulation, PCM. Okay, this is simple circuit about sample and hold. So we take, according to this clock, we can take samples based on the speed of the clock, that it means that the sampling rate. And once you take each sample, each sample can be held based on this, the capacitance of this capacitor. So then we have what is known as pulse amplitude modulation, and the signal, this is the red one is the original signal, and the black one is the sample and hold signal at the output. As we increase the sampling rate, of course, we can increase the accuracy of the output pulse amplitude modulation. Okay, and the analog to digital converter, we have different kinds of analog to digital converter. This is one example, very basic digital to analog converter. The idea is very simple in this one, even it is not efficient, and as we will see, it is good for slow or for low sampling rate case. But in general, that's how it works. That we have counter here. So the counter is counting, like for example, according to some sequence. Let's say it accounts with linear shape. So it is, for example, 0 0 0 0 0 0 0 1 and 0 0 0. For example, 1 0 and so on. So this counter will count every clock. So once it is toggled here every time, so it will count one step more. Okay. What we have here, we have our analog input signal. So it is here. So if the analog signal, assume that now the counter is cleared. So all inputs are at its minimum value, whatever was the minimum, how we define the minimum, if it is all zero, or maybe the last digit, we keep it to represent the sign of the signal, plus or negative, positive or negative. So if it is in that way, so it might be different, the representation. But let us assume that the minimum of this distance is defined as all zero output. So it is cleared to all zero output, and means that digital to analog converter here, it can be realized with the series of resistors. It is quite easy to implement the digital to analog converter. So the output here, assume that it is zero. For example, we assume that the minimum of this signal is zero, and once the input signal is greater than zero, what happened? Here we will have positive, like plus one, for example. Once we have plus one here, so it means that this AND gate will be opened, and according the output here will be one or zero based on the clock. So the clock here, it gives us like the clock. Uh, Sorry for this. Yes, this is the clock pulses. So each clock pulse, it will make here on and off, and then the counter is counting, and the data, the output will be increased in a ramp way. Okay, and assume that the counter is increasing step by step, until the moment that the output here x becomes at certain time, at certain value, greater than v input. Once x is greater than v input, then this comparator will be switched to -1 or to 0, which means that it will switch off the AND gate. So even for the clock, whatever was the clock value, the output here will be always 0, which means that there is no counting anymore. Okay, and this 0, it goes to the control signal, or sorry, control block, and in the control block it will make two like tasks. The first task, it will ask for the latches to read the value of the counter output at this moment, and after that it will clear the counter, and then we start again for the second sample. So the output here will be the digital output, which is representing the input v input. Okay, so you can see that it is very simple to implement. It can be implemented easily, even in like a first course in logic analysis, for example, in laboratory. But the problem that this one is not suitable for fast application. The reason, assume that if we have like 8 bits counters, it means that it will count 256 times. So if the sampling rate of this signal, the original signal, if we want to have the sampling, like for example every 1 microsecond, okay, so it means that every 1 microsecond we need to count 256 times, because the signal can be just the worst case, that you start from 0 0 0 0 0, and but the signal is at all once. So in that case we have to always to wait 256 times within 1 microsecond, which means that the clock rate should be 256 times the sampling rate, which is 1 over 1 microsecond, which means that it's 256 mega like bit per second. So it is very 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 like large bit rate or clock rate, in order to get this to convert 1 microsecond. What if we want to have 10 bits accuracy, So in case of 10 bits means that about 1000 times, more than 1000. And if the sampling rate again is 1 microsecond, it means that the clock rate should be at least 1 gigabit per second. This is doable, but it is not like a simple, or is not cheap, that the circuit that it can work at a clock rate of 1 giga or 10 gigabit per second. So there is another simpler analog digital converter. It is called flash converter. Um, Here the cost is higher because it needs many comparators inside this integrated circuit, but it is much faster. The idea here is that you can see this is the analog input. It is given at this, the positive side of the comparators. Okay, and then we have some reference voltage which is divided over all these comparators. Okay, and now assume that the analog input is very small. Okay, is the minimum, which means that it is less than all the other inputs here. You can see that the voltage here, for example, is less than the voltage here, and the voltage here is less than the voltage here. And sorry, as you are closer to the source, then the voltage will be higher. So the voltage here is higher than the voltage here, and the voltage here is higher than the voltage here, and so on. Okay, so this will be the minimum voltage. So if the analog signal is less than even the minimum voltage, what will happen? The outputs of the comparator all will be zeros or minus. Okay, and then the encoder logic will know that the input analog signal is, for example, all zero. Okay, and now if the analog signal is greater than this V but less than the others, then only the output of this comparator will be plus, and the others will be minus. Then the logical encoder will give the right value of the digital format of the input signal. So it depends on the input signal value or voltage or level. The output will be of the digital output. So uh, you can see that we don't have any counter to count in order to compute the right output, and then it is done in parallel. So it is much faster than the previous ramp digital to analog converter. However, that the only complexity here is in the cost. For example, if you want to have 1000 level, which means that 10 bits, more than 1024, and it means that here you should have 1024 comparator inside the integrated circuit. But right now, with these advances in integrated circuit fabrications, it is not that hard as before, let's say 30 or 40 years. Now it becomes available and at a reasonable price, not very costly. Okay, the sampling process, you can see that mathematically we can represent the sampling that as a multiplication of our original signal by train of impulses, as you can see. Then we will get this train of impulses where the area under each impulse is the same as the magnitude of the analog signal. Okay, now if the this analog signal, it has, we assume that it has this shape in a frequency domain. This is a frequency transform of the original signal, or the post-spectral density of the original signal. It becomes like that, and then when you have a train of impulses, the Fourier transform of a train of impulses will be also a train of impulses in a frequency domain. Okay, but the frequency here will be fs, and fs is the sampling frequency, which is 1 over ts. Of course, here we have here ts, 2ts, 3ts, and so on. This is 0, this is minus ts, and so on. So now the sampling frequency is 1 divided by ts. So this will be also train of impulses. Okay, I don't want to take you into like deep mathematical analysis for this one, but simply that the multiplication in time domain is equivalent to convolution in the frequency domain. So now you need to convolve this signal with this train of impulses, and simply when you take the convolution of a train of impulses, any signal with impulses, then it will be shifted by these impulses. So the first one, it will be shifted by the first impulse, but the first impulse is not it is at frequency 0, so the first will be the same. The second one will be shifted by fs, and the others will be 2fs, and the others will be minus fs, and so on up to infinity. This result is very important in sampling theorem because it indicates that, at least in ideal sampling, that the sampled version of the signal will be simply the repetition of the original Fourier transform of the original signal repeated by the sampling frequency as it is shown here. If m is the maximum frequency or the bandwidth of the signal. Okay, so in order to avoid any distortion of the original one, because actually we are very interested in the first one here, because this one that we will retrieve later when we make from digital to analog converter. When we repeat the original signal, we don't want this one to be distorted. Okay, so in order to preserve this one from distortion, we have to keep certain sampling frequency. So the sampling frequency must be greater than to the maximum frequency of the signal content or the bandwidth of the signal. So this is very important result in sampling theorem. So you can see here that if the sampling frequency is exactly the same as double of the FM, the maximum frequency component in the low bandwidth signal, you can see that this will be the spectrum of the sampled signal, which means that we can retrieve our original signal by using ideal low pass filter. If s is even greater than 2fm, it will be even better, because now you can see we have some frequency between the spectrum, so it becomes easier. Even if we don't use ideal low pass filter, we still able to retrieve our original signal. In case that if the sampling frequency is less than double of the maximum frequency of the signal, then we might have this aliasing distortion. Okay, as you can see, where part of the signal can be distorted according to the percentage of the signal. This is assuming that the signal is uniformly distributed. Okay, so in that case, the signal can be distorted in this way. Okay, now you can see here that we have the pulse amplitude modulation. Just to revise the previous part, so we sampled the signal, or we quantify the signal in time domain. We divide the signal into different samples, and then each sample is rounded to the closest level, allowed level, and then we convert everyone to its BCM sequence. So it is 001, this one is 110, and so on. So from analog signal, we take sampling, and we take sampling in frequency, quantization in level, and then conversion to the BCM. And now we can assume that, for example, this is in 3 levels, for example. Then we have 0, 0, 0, 0, 0, 1, 0, 1, 0 until 1, 1, 1, and each one can be seen as a symbol of the output. For example, this could be S0 until S7, or it depends on the modulation type. Okay. If we take the simple example, so if you have analog signal with 5 kilohertz as maximum frequency, and the signal is sampled, then quantized to 128 level. So 128 level means that it is 7 bits, because 2 of the power n minus 1, it gives you the number of levels, not included the zero level. So and 2 of the power n is equal to 208. Okay, which means that n is equal to 7, because 2 of the power 7 is 128. So it is 7 bits. Okay, now the sampling frequency should be more than double the maximum frequency, which means that we need the sampling frequency to be 10 kilohertz. This is the sampling frequency, or 10 kilo sample per second. Each sample converted to 7 bits, which means that now the bit rate is 7 times 10 kilo, which means that it is 70 kilobit per second. Okay, Now, as I mentioned before, that the number of levels determine the accuracy of the conversion, and we represent the round of error due to the quantization as noise. So the signal to noise ratio, the peak signal to noise ratio, can be derived easily as 3L square. L is the number of samples, the number of levels, sorry, the number of levels within the range. Okay, so as you have more number of levels, then you will have more signal to noise ratio, signal to quantization noise ratio. Okay, and actually the signal here is computed as it is peak signal power divided by the average noise power of the quantization process. So it is given as 3L square. Okay, it means that, for example, if you have L equal to 100 level, then the signal to noise ratio is 3 times 100 square, which means that it is 30,000. Sorry, it is 30,000, the SNR. Usually the SNR is computed in terms of dB, decibel. So we take 10 log this number and we give the number in decibel. Let us take an example. How many levels required to achieve the signal to noise ratio in dB equal to 50 dB? How many? Now we can convert first from dB to the linear scale. So you can see that here that 10 log 10 of the SNR is equal to 50 dB, which means that the SNR in linear scale equal to 10 of the power 5. So you can divide this 50 by 10 equal to 5, and the reverse operation of the log 10 is 10 of the power. So it becomes 10 of the power 5, and then 3L squared equal to 10 of the power 5, which means that 100,000. And then you can compute L, and L here should be at least 183 in order to get this 50 dB. Okay, and how many bits that we can compute is simply you can take, as I mentioned, it is 2 of the power n number of bits equal to here the number of levels, which means that n equal to log, for example, for basis 2 of L. Of course, log for basis 2 of L, if you don't have calculator with log 2, you can calculate it like this. Log, for example, for basis 10 for L divided by log for basis 10 for 2. It will give you the same result. And this gives the number of bits. So the number of bits, for example, if the number of bits was 7.2, we don't have zero point 0.2 bits. So what we can do, you can just take the closest integer number above this one. So here we have 8 bits, or the roof of the numbers. Yeah. Another example, what is the BCM bit rate required for a system of monitoring a chemical reactor? The minimum time for the reaction, so the time that we want to see that reaction, is done within 1 microsecond. Okay, and we need SNR to be like 60 dB. 60 dB. Okay, of course, since it is 1 microsecond, that this is the time, which means that the sampling frequency should be the double of the sampling time of this chemical reaction. The chemical reaction highest rate is 1 megahertz, because it is 1 divided by 1 microsecond, which means that it is 1 megahertz, and the sampling frequency should be at least double that frequency, which means that it is 2 megahertz. This is the sampling frequency is 2 megasample per second. Okay, now we calculate the number of levels required to achieve the 60 dB. Then again, as we did in the previous slide, L should be greater than or equal to 10 of the power 6. This is the number this is the SNR. So we take it from dB to the linear scale, which means 10 of the power 6, divided by 3, because here 3L squared should be greater than or equal to 10 of the power 6. This gives us 3.33 times 10 of the power 5, and then we can calculate the number of bits as shown in the previous slide. It gave us 19 bits. So we need 19 bits to represent this signal. And now the required bit rate will be 19 times 2 times 10 of the power 6, because this is 2 megahertz. Then it gives us 38 megabit per second. Please remember here that when we calculate the SNR, we assumed like uniform distribution of quantization. So it is linear quantization. In many situations, we use nonlinear quantization, which can give higher performance. So, for example, if the signal is not uniformly distributed over all levels, so we have levels, but the signal is 90% or 80% is within smaller range of amplitude, then there is no need to use uniform distribution of the quantization. We can have higher quantization levels, or smaller smaller intervals where we have higher possibility that the signal is changing within that range. And in that case, we can get, for example, the same 60 dB here, but at less than L number of levels. So with using nonlinear with optimized distribution, we might get much better performance. And digital modulation, where, as we mentioned before, we have amplitude shift keying, frequency shift keying, phase shift keying, and quadrature modulation, or amplitude phase shift keying. In binary digital modulation, of course, binary means that we have either symbol 1 or symbol 0. It is like 0 or 1, but it is also possible to send more symbols than only two symbols. So we can, for example, have four array. Means that it is four symbols. For two symbols, we call it binary, and they take this array at the last of binary, and then we have 4 array or 8 array or 16 array. Usually it is in double of 2 or 32 arrays, and so on. So we can have if 32 means that we send 32 symbol. We have 32 symbol, and each symbol in this case represent one of 5 bits. So each symbol can be represented by 5 bits. And we will see later the benefits and limitations of using higher number of symbols in the transmission. So this is the S0 or S1. This is the binary case. And how to select the symbols? Usually we should select the symbols to be so they as dislike as possible of each other. So we have to keep them as dislike as possible, because we don't want the receiver to confuse between which symbol was transmitted. For example, if we send this as symbol 0, this pulse as symbol 0, so what you think, how it will be the most dislike symbol to be transmitted within this time is 1. Of course, it will be the reverse of this symbol. So if the symbol is like +1, then this one will be -1. So this will be 180-degree shift from the previous one, which means that it is the most dislike signal that you can send within this shape. Okay, and let us see the benefits of using antibodal signals like +1 and -1. For example, if we assume that we have two signal, S0 is represented by +1 volt and S1 is represented by -1 volt, and here we ask to how to compute the average transmit normalized power if both symbols are equally likely. Okay, and now we assume that if we have S0 equal to 0 volt and S1 equal to 2 volt, so you can see, compared to those, actually the performance in terms of quality is almost the same, because this one is +1 and -1, so the difference between them is 2, and here is 0 and 2, and the difference between them is still 2. Okay, so if you want to compute just the probability of error, or or the confusion at the receiver, the performance in that sense will be quite similar. But let us see what is the average power required to send +1 and -1 or to send 0 and 2. The average power to send a +1 or -1 will be 1 watt. You can see that it is 1 square because this is normalized power. It means that we divide by R, but R equal to 1. So the average power will be +1 square times the occurrence, probability of occurrence of +1, and we said that is equally likely, which means that we multiply them by half, or plus -1, we divide them by half, so the average power will be 1 watt. Now, if for the second case, it is 0 squared times half is 0, plus 2 squared times half is 2 watt. So actually, 0 and 2, it will need to, double the power in order to get the same performance. So this is the reason. This is very big difference, by the way, when we talk in communication. In communication, one of the major targets or major objectives is to use the minimum possible power to achieve the required quality of service. So this is important that to save power, and you can see that this will need double the power. So the case of using antibodal modulation is very important and very desirable. It gives very high performance in terms of probability of error. Okay, so binary digital for modulation. Okay, now let us stop here about the binary digital modulation, and we start them in the clip 3 of this part. Thank you very much, and see you.